Okay, let's go on. I've copied the formula from above, this prox operator, and the idea is now to replace this by something which is independent from the parameterization. Notably, the Kullback-Leibler divergence between two distributions. And in what follows, I'm taking the argument which has been written up, for example, in a paper by Desjardins and by Pascanu. I don't remember the titles, but it's something natural in the title, probably. Good. So the idea is that the metric tensor of the neuromanifold will be given by the Fisher information matrix. Yeah?
Just a question about the formula up there. I mean, shouldn't it be, because on the left, the first instrument, you use the phi star as like the difference, and then the second one, you use it as the new one. Shouldn't it be?
I use it as the difference?
I mean, because shouldn't that be like a delta phi? Wait, shouldn't it be a delta after? You know, before the plus sign. I have a hard time describing what I mean.
Yeah, no, I think I get what you mean. Let me think. So you're asking why there is not a minus theta t or something there.
I mean, just in the end brackets.
Yeah.
So otherwise, this would be minimized also if just the V star is small.
Isn't that a dot product there?
It is a dot product.
Okay. Yes. Oh, sorry.
Okay, let me just try and do that, and we see if the correct thing falls out. Yeah. So I want to differentiate all this with respect to theta star, and I'm getting dl by d theta transpose plus 1 over mu, and then we have the plus theta t minus should be a 2 here, theta t, and then we have the theta star, and this derivative should be 0, and then I get that theta star equals mu times the loss minus theta t, and I'm not happy with the sign yet. There should be a yes, so this should be a plus, and then I get a minus here and a plus there. And that is the formula that we usually get. And you're asking why not, so why have an absolute and not a relative vector there? Well, it pans out. So the first term gives me the direction, and the second term gives me the relative add-on and the length. But I mean, if you agree with what's written on the right-hand side, then who asked the question, by the way? Sorry. Okay. So if you agree with what's written on the right-hand side, then we simply find equivalence between this prox version and the original gradient descent, and we wanted something that's equivalent.
All right. I was just wondering because we usually have like the gradient times the step, and the step is the difference. So in this step is the absolute value. So
More questions? So I'm satisfied by the thing coming out correctly. Yeah? Okay. So we will take as dissimilarity measure the Kullback-Leibler divergence. Between some distribution parametrized by theta and some distribution parametrized by theta plus an increment of phi. So phi is a small change of the parameters, and it's defined as follows. And I now want to show in a few lines that this can be approximated by a bilinear form where F is the Fisher information matrix. Okay? And the idea is that this dissimilarity measure between distributions will no longer depend on the specific parameterization used. So I'm starting by, so we have a logarithm of a quotient. So I'm separating that into two terms, one of which is subtracted from the other. Log d theta of z minus okay, in this second term, because phi is small relative to theta can now be Taylor expanded. It will be very modest here into this to first order only. Again, the gradient here is a row vector and phi is a column vector, and we ignore higher order terms. And now with this approximation, we see that, okay, let me write one more line here. I copy the first term, and now for the second one, we have the integral of p theta of z times the logarithm of, and I'm multiplying out p theta of z, and now multiplying this with 1 plus and because there was nothing, I mean there was no multiplier of p theta of z here, I need to divide by it. And this in turn gives me this. And the point of this effort was to let these first two terms cancel now. So this one and this one, the expected log of this distribution cancels. And we're left with this last term, where now another approximation is used, namely the following. So the log, the second term here is small compared to 1, so log of 1 plus epsilon is approximated as epsilon minus epsilon squared plus epsilon to the third divided by 3, and so on. Okay, now with this second approximation here, we get the following. So I need to write this, what was the epsilon, the argument here. Now we need to go to second order. So I divide by 1 over 2 p theta z squared. And now comes a bilinear form. So I have phi transpose. Okay. And now we had I can on the one hand always add 0, which I'm doing now. So I am taking here the integral over probability distribution, which has a mass of 1, and then I am taking the gradient thereof. And the gradient of this constant 1 is a vector of zeros, and this vector of zeros I'm multiplying with phi. And on the other hand, we have an integration with respect to z, but these phi's do not directly depend on the z's, so I can pull them out. So this was the first term here, yeah, where the integration was with respect to z, but the gradient was with respect to theta. Yeah? And so subject to some regularity and hand waving, we can pull this out, and that gives us the thing on the bottom. And now for the remaining part, I pull the phis out. So we have, let me check the sign. We had a minus here, and then a minus inside gives a plus of 1/2. And now the integral. Okay, now a final trick, namely, if I have the gradient of the logarithm, then this is exactly the same here, because I get 1 over p times the gradient of p, which is what you see up there. So this whole thing can be rewritten in the end. And there's still a mistake somewhere. I have lost a yes, I lost the multiplication with p of theta. So here. Okay, now this can be written as an expectation. Namely, the expectation with respect to z of the gradient of the, so the gradient of the log likelihood is the score. And I've lost the phi's. Phi transpose here and phi there. Good, and this thing here is now called the Fisher information matrix. Which emerges as a local approximation to the Kullback-Leibler divergence. Okay, and now we can use this prox operator. So we can say that theta t plus 1 is theta t Let me scroll back up to see if I had made an error before when trying to answer your question. No, I don't see any. So this time we say that theta t plus 1 is the minimizer The difference is that the minimization now is only over phi, not over theta. And this is why I need to add theta t here. And this is what I was just irritated about. Okay, so this time we're looking at the increment. Yeah? So we have the argmin of, on the one hand, the loss. For a given training set. And on the other hand, Kullback-Leibler divergence. And this we have now approximated by phi transpose F phi. And if we now take the derivative with respect to this phi star and so on, then we finally find that we should multiply with the inverse of the Fisher information matrix. Okay, and this is now parameterization independent at last. So we started from a dissimilarity measure which directly depended on the distributions and not on the ways, depended directly on the output distributions and not on the way that these were parametrized. Now, what's good about this? We don't actually need the training labels. Because the true labels do not appear. We simply see how strongly does the output distribution change if we change any of the parameters in the model. What's bad? And we have this parameterization independent descent direction. What's bad is that for a real neural network, f is huge, so we cannot even store f, and inverting it is also too expensive, is prohibitive. And moreover, f, if we don't have many input samples, even unlabeled ones, can be difficult to estimate reliably because there are some subtle effects here. We can look at the empirical Fisher information matrix. For this, we sum over all the examples in the training set. And then we estimate the expectation of over y for a given input xi. And because we're using the same samples to estimate the gradient and the same samples to take this to approximate the what is it called? The E bar here, the estimator here. We are using the same samples twice to estimate two different quantities, and that can result in numerical difficulties. There is another form for the Fisher information matrix, and this paper by Pascanu also shows how to derive this second form. Just see if I find it. So the second form is in terms of curvature of the log likelihood. Okay, this takes a longer while to show. Okay, so what we get overall is a rectification, if you like, of this local coordinate system. Yeah, so this Fisher information matrix allows us to estimate how big the impact of changing one parameter will be, and it also takes into account what are the interactions between different parameters. And we get here, on the one hand, a descent direction from the reduction of the loss, and then on the other hand, we multiply with this inverse matrix, which can be seen as making our coordinate system locally orthonormal. Yeah, so if we have some parametrization, I can interpret this action of the Fisher information matrix to make this a nicely orthonormal coordinate system in which the gradient descent direction and the natural gradient descent direction would then coincide. And because f is so large, there are many approximate methods that do not compute the exact f, but approximate versions thereof. So for example, in a deep neural network with many layers, we have a huge Fisher information matrix. And one possibility is, if these are different layers in the network, to approximate this with a block diagonal structure, and to say that we simply pretend that outside the block diagonals, this Fisher information matrix is 0, and then we only estimate it more reliably in those blocks. Another possibility to correct, at least for affine distortions of the coordinate system, is to use the Hessian matrix, but the Fisher information gives us immunity to transformations or to reparameterizations beyond affine ones. So this is more powerful. And like I said at the outset, many of the tricks that are really used today can be shown to make this Fisher matrix better conditioned. So many optimization tricks make F more diagonal. And with F being more diagonal, the consequence is that then just using the gradient direction will be less bad, yeah? Because F minus 1 will then have less of an interesting structure. Good.